Hi guys, welcome back to another video. Today we're going to be solving some questions on quantum mechanics, and those are going to be from OCR Physics A. Just the usual disclaimer, these are not official solutions, these are just my solutions to these problems, and please visit the OCR website for the official papers and the official mark schemes. All of the links to the questions are available in the description, and probably the best way to tackle this video would be to try and solve the problems yourselves first off, and only then look at my solutions. Well, let's have a look at the first question. So we have an experiment that is observed that when blue light is shown on a clean metal surface, electrons are emitted, but when red light is shown, there is no electron emission. State the name of the effect observed in this experiment. Well, this is a classic example of the photoelectric effect, so we can just write that in, photoelectric effect. Now, the next one here describes Einstein's theory to explain those observations. In your answer, you should include technical terms. So, okay, we're going to be describing some technical terms. As soon as I read technical terms, I think about the work function, the threshold frequency, for instance. So I'm going to make sure to include those in our answer. Also, in terms of photons is also another technical term. So even when I'm sort of writing this, I'm just going to write these. I'm going to write work function, photons, just as a reminder that I need to use all of those words, and how the physics of quantum behavior is used to explain those observations. Okay, well, let's tackle this 4 marker. In this question, and in general in the photoelectric effect, only photons with energy higher than the work function, this is really important, will actually cause electrons to be emitted. Blue light has photon energy above the work function, and therefore electrons are emitted. Red light has energy below the work function, so electrons are not emitted. The reason why blue photons have a higher energy is because they have a higher frequency. So remember, the energy of a photon is equal to hf. So if your frequency is higher, because h is a constant, then your photon energy is going to be higher. Einstein's theory also says that there's a one-to-one interaction between the electrons and the photons. This whole result is governed by Einstein's equation, which says that the energy of a photon, hf, is equal to the work function. So some of that energy goes into the work function plus the maximum kinetic energy of the photoelectron. Part C, the longest wavelength of light incident on a metal surface which causes electrons to be emitted is 480 nanometers. Show that the work function of the metal is about 4 times 10 to the power of minus 19 joules. Okay, well, our work function phi is just energy. And because it's just energy, it is equal to Planck's constant times the threshold frequency, because in general the energy of a photon is equal to h times f naught. You can kind of think of the work function as threshold energy. Because frequency is equal to the speed of light divided by the wavelength, we could also rewrite the same equation in a more useful format for this particular question as phi, the work function, is equal to hc over lambda. So we know what h is, given in our formula booklet. We know what the speed of light is as well. We know what the wavelength is. We can directly solve for the work function. So the work function will be equal to Planck's constant, which is 6.63 times 10 to the power of minus 34 times the speed of light, which is 3.0 times 10 to the power of 8 meters per second. Then we're going to divide this by the wavelength, not forgetting to convert the nanometers to meters. So that's 480 times 10 to the power minus 9. Like so, when plugging this into a calculator, we are going to get 4.14 times 10 to the power of minus 19, which is about 4 times 10 to the power of minus 19 as required by this question. Okay, part 2. Calculate the maximum speed of an emitted electron when a photon of energy 5.2 times 10 to the power minus 19 joules is incident on the metal surface. Okay, well, this is a direct application of Einstein's equation and then the law of kinetic energy. So I'm going to write down Einstein's equation here. That tells us that HF is equal to 5 plus KE max. So because we're looking for the speed of the electron, we're going to need to know its kinetic energy, and HF is already the energy which is given. So this whole quantity HF is the energy of a photon, which is 5.2 times 10 to the power minus 19 joules. So this means that Kmax, like so, will be equal to HF minus phi, and HF is the photon energy once again. That's 5.2 times 10 to the power minus 19. Take away the work function, which we found this previous question to be 4.14. Because we're dealing with a significance of 2 sig figs, let's use that. Minus 4.1 times 10 to the power minus 19, and this will give us 1.1 times 10 to the power of minus 19 joules for the kinetic energy. What I'm going to do next is just use the equation for kinetic energy to solve for the speed of that electron. So I'm going to say that K max is equal to half mv squared, which means that v will be equal to the square root of 2ke max divided by the mass. So this will be equal to the square root of 2 times 1.1 times 10 to the power minus 19 divided by the mass of the electron, which is given in our formula booklet, 9.11 times 10 to the power minus 31. And if we put that into a scientific calculator, we are going to get about 4.9 times 10 to the power of 5 meters per second. Next one, describe briefly one piece of evidence for believing that electrons sometimes behave like waves. When electrons pass through a thin graphite sheet, it has to be a thin one actually, because otherwise you're just going to get an absorption of all of the electrons. They will produce a diffraction pattern, which is a pure wave-like phenomena. This is one of the most interesting experiments in physics that really demonstrates the nature of quantum mechanics. This means that electrons can behave as waves, and we can calculate the de Broglie wavelength of an electron at a certain speed. The equation is given in our formula booklet for that wavelength, and that is equal to h divided by p, where p is the momentum of the particle. So this means that lambda will be h divided by mv, and h is Planck's constant. That's 6.63 times 10 to the power of minus 34. M is the mass of a single electron, 9.11 times 10 to the power of minus 31, times the speed, which is 500 kilometers per second. Just underlining the kilo to not forget to include that factor of 10 to the power of 3, so 500 times 10 to the power of 3. If I was to put this into a scientific calculator, I'm going to get about 1.5 times 10 to the power of minus 9. So this is a tiny wavelength. So let's write that over here, 1.5 times 10 to the power of minus 9 meters. Next one, which is about the classic gold leaf electroscope experiment. We have a gold leaf electroscope here, and that's used to demonstrate the photoelectric effect. We've got a zinc plate, which is negatively charged. The electrons here repel the electrons on the gold leaf, and the gold leaf rises. We have some observations over here. We have a light from just a normal table lamp with visible light is allowed to fall on the electroscope from a distance of 10 centimeters. We're given distances. I'm just going to underline or highlight these because these are probably going to be quite important in my answer. So the experiments then repeated with light from a distance of 4 centimeters, and both experiments are then repeated with ultraviolet radiation. One thing that I instantly just going to write down is that the smaller the distance between the lamp and the plate, the higher the intensity. So it means higher intensity, which in turn means more photons. And this is something that I'm going to be including. Even as I'm reading this question, I'm thinking about the one-to-one interaction, how this will affect the experiment. Okay, now moving on, we have the observations which are recorded. We're using just normal visible light at a distance of 4 centimeters. The gold leaf will take a very long time to fall. The reason for that is just through normal electron discharge, so it's just going to be discharging incredibly slowly. So ultraviolet radiation, distance of 4 centimeters, the gold leaf will fall quickly or very, very quickly when we are at a distance of 4 centimeters and there is a higher rate of falling. Explain these observations and see how they demonstrate the photoelectric effect and provide evidence for the particulate, means essentially the particle nature of EM radiation. Okay, let's do this. So a pretty important tip that I can give you guys is to structure your answer in accordance to what is required in an extended writing question. For instance, if you're asked to do two things, such as this case, in which we have to explain and then provide evidence, it'll be far easier for this question to be understood and marked well if we have two sections, one with an explanation and one with some evidence. Okay, well, let's start off with the explanation first. The fall of the gold leaf is due to the emission of electrons. So we're going to start off with the full-on basics of this question. The idea here is that UV photons have energy above the work function and hence cause electrons to be emitted. When you decrease the distance, this means that you are increasing the radiation intensity. So there's a greater rate of photons which is being incident. At 4 centimeters, the intensity of UV radiation is higher. So as I said, this means that there's a higher rate of incidence of photons. In other words, if you're decreasing the distance, you are increasing the rate of incident of photons. Therefore, the gold leaf is going to fall quicker. You can kind of think of it as essentially if more photons are arriving, then more electrons are going to be discharged. That's why the gold leaf falls very quickly at a distance of 4 centimeters compared to distance of 10 centimeters. Now, light photons, visible light photons from just a normal desk lamp have energy below the work function, so no electrons are emitted, regardless of the distance and regardless of the intensity. Therefore, normal light has absolutely no effect on the discharge whatsoever, and in fact, the gold leaf will just be discharging naturally. Now that we've done the first part out of this 6-marker question, let's have a look at explaining how those observations provide evidence for the particulate nature of electromagnetic radiation. In other words, how does all this tell us that a light can behave as a particle? Now, the first thing, and this is really, really important, is that, in fact, I'm just going to highlight this over here, but according to wave theory, the gold leaf should fall at a higher rate with visible light. So this is really, really important. And in fact, visible light has absolutely no effect whatsoever on the gold leaf, whereas UV radiation causes almost instantaneous discharge, whereas wave theory predicts it will take longer. And these are some of the most important points of this experiment that really prove the particle nature of EM radiation. Additionally, we can also infer that there's a one-to-one interaction between photons, and each of those photons has an energy of hf and electrons. That's why the rate of flow increases at higher intensities, because there are just more electrons interacting with more photons. The reason why nothing happens when we shine visible light is because UV has a higher frequency than visible light, and it's above the threshold frequency. The interactions once again obey Einstein's equation that hf is equal to the work function plus K max. Okay, on to the next question. Okay guys, on to the next one. Remember, all the questions have links given to them in the description of this video. So, state one experiment for each case which provides evidence that the electromagnetic radiation can behave like a stream of particles called photons. Well, the photoelectric effect definitely proves that, so I can write that in the photoelectric effect. Please note that this is uh, the general effect that shows that light can behave as particles. So we shouldn't really write the gold leaf electroscope. We have to be more specific than that. We should write the photoelectric effect and state another experiment for each case which can provide evidence that EM radiation can behave like waves. For instance, Young's double slit. So Young's double slit, which of course showcases interference, which is a purely wave-like property. So the next one, we have a pretty standard definition here. Define the work function of the metal. Well, that is the minimum energy required to release an electron from the surface of a metal. It is the minimum, and this is quite an important word, so that's why I am highlighting this. Okay, right, so we also given a graph of kinetic energy on the y-axis and frequency on the x-axis. For part 2, we need to write down the relationship between K max and the frequency, and then we also need to use that to explain why the intercept is equal to the work function and the gradient is equal to Planck's constant. Well, let's do this. The relationship is given by Einstein's equation, which is hf is equal to phi plus K max. Now, what we need to do is rearrange for K max because that's on the y-axis, and then use y is equal to mx plus c analysis. So just doing that, we're going to get that Ke max is equal to hf minus phi, and we can then perform y equals mx plus c analysis directly underneath. So we can write down y is equal to mx plus c, and we can see that K max is on the y-axis. Our intercept will be the negative work function, so this is really important, and our frequency is on the x-axis, which of course leaves the gradient m. So I'm going to say that the gradient m is equal to Planck's constant, and our intercept c is equal to minus the work function. So it's the actual absolute value of the intercept that is the work function. Okay, use data from figure 7.1 to find a value for the Planck's constant. So we can use the fact that our gradient m is equal to delta y over delta x, and remember, we're going to need to try and make our gradients as large as possible, and delta y is, we're going to go from 0 to about 40 times 10 to the power of minus 20. Let's try not to forget about those units. This is probably the trickiest bit. And on our x-axis, we are going to use this distance from here, from 15 times 10 to the power of 14 hertz to right about there. And that distance is 6 points, a little bit more than 5. If we count those carefully, we're going to get about 6.30, or I'm just going to try and be a little bit more precise. I'm going to write 6.25 times 10 to the power of 14 hertz. Now, plugging that into a scientific calculator, our value for Planck's constant is going to be 6.4 times 10 to the power of minus 34, like so. Let's just write that in the box. So 6.4 times 10 to the power of minus 34 joule seconds. So for the next part 2, we need to calculate the threshold frequency of the metal. Well, we can directly get that from the graph. This is actually this x-intercept here. We're going to see that there's absolutely no kinetic energy, there's no electron emission until we reach that specific frequency. If we look closely into it, that's actually 8.75 times 10 to the power of 14 hertz. So I can directly write this in. So it's 8.75. Please don't forget the power here times 10 to the power of 14. Once we have the threshold frequency, we can also use that to calculate the work function just by multiplying that by Planck's constant. So I'm going to write that 5. The work function is equal to Planck's constant times the threshold frequency. So this is going to be 6.4 times 10 to the power of minus 34. Notice that our calculated value from this data is different from the value of Planck's constant, which is given in our formula booklet. However, because our question says use data from the figure, I'm just going to stick with 6.4 times 10 to the power of minus 34. Then I'm going to multiply that by 8.75 times 10 to the power of 14, and plugging this into a scientific calculator, we are going to get about 5.6 times 10 to the power of minus 19 joules. Okay guys, so we finished this question. Hopefully this video was useful. If it was, please like and subscribe. Thank you very much for watching, and I'll see you in the next video.